So we'll now continue the discussion, and we are now coming to the heart of the topic for today. And we want to see that, the OGIS spatial feature types and so on. But before I go there, I want to also motivate why we should learn those data types. And if you don't learn that, the life is a little harder. Okay. So let me just close the door and I'll start the discussion. Okay, great. So let's probably revisit the life without spatial extension. Okay. So I'm just going to motivate this, and then introduce the solution, which will be hopefully useful. Okay. So generally, these kind of problems were referred to as with different names. One name people used was semantic gap. Another one they said impedance mismatch and so on. Okay. So let's actually look at what they meant. Right. So if I'm going back to 90s, SQL was one of the last languages to add object orientation. Okay. Most of the rest of programming world moved to object orientation in 1980s. Okay, but SQL did not. And the end result was that it just had a fixed set of data types like numbers, dates, currency, and so on. Okay. But if you wanted other data types like points, polygons, there was no mechanism to add it. Okay. But in addition, we had other database design consideration, right? So suppose I want to represent a simple rectangle with 4 corners. There was no easy way to create a data type called polygon or rectangle back then. Okay. This is 20 years ago. But if we wanted to have these applications and do queries like this, suppose I have a collection of rectangles and I want to ask all the rectangles which contain origin as a corner point, right? Or all the rectangles which contain origin as an inside point. Okay, these kind of queries had popped up, for spatial applications as well as VLSI design. And what we had to do was the following. Okay? So a little bit of this will also refer to a database table design conventions. And so let me have a quick show of hand. How many of us know third normal form table design? About half of us. Okay, good. So remember in 1980s, people advocated that, and it has something to do with data quality. Particularly if you have very high update rates, then keeping your data in third normal form reduces redundancy, and it reduces the risk that one copy is updated and other is not. Remember all that, right? So this was very, very ingrained in database world, and they advocated that your table should follow that. Okay, so let's try to think about how I can design a table to store rectangles if I don't have OGIS. Okay. Now in third normal form, let's also remember. Anyone remembers what's the first normal form? What does it say? Atomic values, no multi-valued things, right? So if this rectangle has 4 points, can I collect 4 points together in like one field? Probably not, right? It's multi-valued. So you need to break it up. Okay. So multi-valued attributes are separated as a separate table. So rectangles, would be one table, points will be a separate table, right? Okay. So this rectangle has to be broken into 4 points, a separate point table. And if I want to say there are 4 edges in a rectangle, that also will be a separate table, right? So third normal form is forcing me to make multiple tables. Okay. But is that all I need, or do I need something more than that? You may be considered with ordering, but usually relational databases don't track ordering. It's a set. Sets have no orders. But you need some way to connect. I want to say this point belongs to this rectangle, then you need some kind of a relationship, right? And in general, it's a many-to-many relationship. A point may belong to many rectangles, and certainly a rectangle has many points. So you need another table to connect, points and so on. So here, this table basically says which point belongs to which edge. So like point P2 and P3, they relate to this edge, okay? But P2 also relates to that edge. So that's why it's a many-to-many relationship. It's a separate table. Okay. Similarly, when I'm looking at edge versus rectangle, you may have another table. Okay. So if I don't have object-oriented facility and user-defined data type, in order to represent this simple rectangle, I need 5 tables in third normal form. Okay. This is how people did things back then. Okay. So in order for you to actually show what this table will contain, okay, so here is a rectangle. I had 4 points, they go in the point table. I have 4 edges, they go in the edge table. And so and then this rectangle, these four edges are connected. That's your mapping table. And finally, edge to point table. So edge E1, okay, edge E1 has P1, P2, edge E2 has P2, P3, and so on, right? So these are your tables to represent a very simple thing like a rectangle. Does everybody kind of see what life used to be? Okay. Some of you are already saying, it's big nonsense, rectangle is such a simple thing. Why do I need so many tables? Okay. So people used to give an analogy. It was saying, if your garage were relational, okay, if you had a relational garage, then every, evening when you come back, you want to park a garage, you won't be allowed to do that because your car has 4 tires, right? So in relational one, you have to take the 4 tires, put it on one shelf, then 4 seats on the other shelf. And in the morning, you have to assemble it back. But that's how life used to be. Your application program like GIS, when it gets fired up, it has to join all this table, make rectangles in the memory in your Java object, okay? And when you exit, you have to decompose it back and do that, okay? That's what third normal form life used to be, okay? All right. So there's so much good so far, but now let's think about the programming effort, okay? Now if I want to do simple query, very simple. Suppose I want to list all the rectangles which include origin as a corner point, okay? Then as you can imagine, I have to join all these 5 tables and then impose a condition, right? And the condition probably, would come down here, right? So you're saying point X, okay? So this is not as bad a query. Most of you who have done joins would be able to write it, okay? I would not ask you to do that, but if you are interested, try writing it. So basically all the tables, join conditions, and this condition. You can do it, all right? Let's look at the second query. Of course, this would be a performance challenge. As I said, average programmers, probably this won't be very natural, but people can do it, okay? How about this query? Rectangles with origin as an inside point, okay? Now life gets harder. And those of you who are SQL enthusiasts, I will ask you to try doing it on your own. And if we have plenty of time, we'll show that. But at least I will show you the code. Okay, this is where the pain starts, and this is where that impedance mismatch semantic gap argument was brought. So here again, what you have to do is to join all these queries, and then if you do group by rectangle ID, then you can start picking up the corner points. If I take minimum X, minimum Y, I will get left bottom corner. Maximum X, maximum Y, you will get upper right corner. Okay, and now you can test whether your, the origin is sort of in between the two. Okay. So that's your test, okay? So I'll tell you now, you are well beyond average programmer. I mean, this would challenge a lot of people, okay? Certainly, industry folks didn't like this. And even if you could write it, it's a very expensive query. Joining 4 or 5 big tables takes time, okay? So this is where the argument started building up. And I said by 2003, the SQL met the programming world, and they made it object-oriented. So they essentially said, okay, you can bring in your user-defined data type, and these queries will get simpler. But in order to do that, you have to give up first normal form, in other words, third normal form. Okay. So this is a trade-off. As I said, in SQL, life was tricky, and a lot of programmers complained. It was a very bitter debate in late 80s, early 90s. But today, as I said, this is behind us, and it forced SQL to grow up and become object-oriented. And now you can write code very simple like this. You can have a data type, which is a polygon. You can have operations like within, and you can just write a little code like this, which will be similar to what you would write in Python or Java, right? You will have a class, you will have a predicate, and you will write this, okay? So today, mature SQL looks like this, okay? There are still a few products who haven't caught up. Microsoft dragged its feet till about 4 or 5 years ago, but they caught up. MySQL has also caught up. Maybe they don't have the best indexing yet, but Postgres, PostGIS was an early adopter. So was IBM's DB2 and Informix and so on. Okay, so today life looks like this, and we are going to learn, the OGS data type, which will give you detail of this. Okay, great. So everyone comfortable with the motivation why we are going there and why it may be good to learn. Okay, and as I said, most of you grew up with object-oriented programming, so this is very natural to you. And it's like, my son asked, oh, you didn't have internet when you were growing up. That's sort of the feeling, okay? All right, so let's go look at this OGIS library, which is added to SQL3. Okay, and then we'll show you some examples. Okay, so SQL3 allows any kind of libraries to be added, and many libraries are available, and this list is growing. And the one we are going to look at is the OGIS simple feature type. And this was standardized roughly mid-1990s, and since then there is also an ISO standard which more or less says the same thing. Okay? And this gives you about half a dozen spatial data types. We saw those to you yesterday: points, lines, polygons, as well as their collection. It also gives you a set of spatial operators, and some of those we are going to go through at programming level, and then we'll get into the mathematical underpinning. Okay? It's supported by most interesting vendors that you are aware of. Even PostGIS and MySQL and so on are on board. So the first, let's look at the data types. Its base class is geometry, and then there are few basic class: point, curve, and surface, and then these collections. So 0 dimension, 1 dimension, 2 dimension. And then here these are collections of these things. Okay, so and then there are a bunch of operations. There are some simple operations. These ones, let's quickly walk through them. The first operation actually tells you about the coordinate system the data set is going to use. So remember yesterday we were talking about web Mercator and things of that kind. So whatever data set comes to you, if you had a software supporting OGIS, you can query that and ask them, tell me what coordinate system are you using? Is it latitude, longitude? Is it WGS 84? Is it the Everest, and so on? Okay, so that's available. This is coming from geography side. Okay, this is a very simple operation, envelop, which actually gives you a bounding box, a rectangle around a polygon or a line string. And its origin is more in computer science, because most of the indexing methods in spatial databases are designed for rectangles. Okay, so most computer science software, they don't want to deal with the details of polygons and so on, so they simplify things at envelop and do a filter and refine. Okay, so these are some of the topological operations. You can ask whether a line intersects itself and things of that kind. All right, let's go to the next one. And this is the most interesting set of operations. There is a whole library of topological relationships. So you can use predicates of this nature. You can ask if two geometries are equal. So given two polygons, are they exactly same? Are they disjoint, or do they intersect? Do they touch each other? So if you want to find neighboring countries, okay, this may be the predicate. Cross usually is with a linear part like a river and a country. Okay, within and contains. There is a very slight difference between within and intersect, and we'll go over that. Okay. Yeah, and same way contains. Yeah, so very small difference, and we'll go through that. And then finally, you have some metric operations. So you talked about distance, and in case of distance, you have a choice. You can actually pick a reference frame, and your answers will be different. In a planar one, it will give you Euclidean distance. On a spherical one, it will give you, along the great circle. And at least those two are supported by majority of vendors, but you might even have ellipsoidal and so on built in. Okay, this came up yesterday. So can anyone recall, any computer scientist, what does this give us? This is like geofencing. So if you have a point and you can say everything within a mile of this point, okay, so that gives a buffer of a point is a circle, okay. But you can also do it along a line string. So suppose a river has contaminated water, you can say give me all the areas which are within a mile of this river, okay, or a polygon and so on. Okay, that's what it is. Then here are some simple things. You can do geometric union or intersection of polygons and so on. This came from computer science, not as popular in GIS side. And this essentially, if you have a collection of points, if you put a rubber band around it, sort of think about what the outer polygon would look like, and that's what a convex hull is. This again has a very nice algorithmic property. So many algorithms can be speeded up if you have convex hull. This is sort of dual of envelope. So it's coming there, and then symmetric difference is a set operator, related to that. Okay. So we will spend a little more time to look at mathematical underpinning of that. But before, I want to show you a simple, collection of queries and SQL select statement, how we use them. Okay. So again a quick recall here. So suppose I was going back to the query where I was looking for this origin as an inside point of rectangles. So which operation we will use? How many think it's cross? Okay. How many think it's equal? Contains? Okay, quite likely. Touch? No, okay, and within, okay, good. So it's either contains or within, and we'll know the difference soon. Okay, all right. And I told you again, this is widely used standard today, so it's a good one to learn. But one thing to be careful about is the syntax. There are slight differences from one vendor to the other, even though conceptually the ideas are the same, but the syntax may be differ slightly. Okay. All right. So what I'm going to do is kind of use one simple syntax, but if you don't take this code and run it on different software directly, you may have to adjust it. Okay. All right. So first use, these special data types can be used inside create table, and you saw that a little bit already. But we'll spend a lot of time how you use the operators in select and so on. Okay. So let's look at some of the examples. Okay. So the simplest one. Okay. The simplest operations are unary operations like area. Okay. And these can be used very much in your select clause or a where clause and so on. Okay. Then we'll use the binary operations such as distance and so on. And then finally we'll go to joins and we'll use spatial joins. So let's continue. So here is the first example. So we are looking at name, population, and area of each country listed in country table. Okay. And the key thing you might remember from the schema was that the country table did not have a column called area, right? So you have to now think about it, but we have an operation called area, and country table did have a spatial column called shape. So you could apply area operator on the shape to get the value. So this is sort of the hello world. We take the country table, okay, one table. Name and population are sort of there. So name and population we got from the table, but the area operator was used to derive area out of shape. Okay. And just like in other select clauses, you might have used arithmetic operator or string operator. Now you're using spatial operator, right? Everyone comfortable with this? This is like the hello world for spatial SQL. It's a very small step from, if you know select statement, it's just small change. Yes, go ahead.
When we talk about shape,
right,
in the table it only mentions something like a polygon.
Yes, yeah.
But for area you need dimensions, exact, if you want to calculate the area. So how does that work in this case?
Okay, dimension you're thinking about, can you say a little bit more? Is it 0, 1, 2, 3 dimension, or you're thinking about units? Or?
I'm talking, let's say, even if you take, for example, it says a polygon is a rectangle.
Right.
So that is what is the identity as far as table is concerned.
Right.
But each side being 5 by 5 or 4 by 4 to calculate the area.
Right.
That has to be factored in. How does that come into play?
So this is a very interesting question. I'm trying to interpret what it is, but one thing you have to realize about SQL and contrast it with Java, Python, and other language is that SQL is declarative. And in a declarative language, we don't actually specify how it will be computed.
No, I'm not talking about the how we compute it.
Right.
But there has to be figures to compute the areas.
Okay, it's in the table.
It's because the
Okay.
polygon is the set of points.
Right.
So
Ma'am,
probably
agreed, but what happens is in a country
It's
case
not
it is irregular. It is not a perfect geometric
Yeah.
shape. It is an irregular polygon.
Right.
yeah.
Right.
So there has to be some biomedia to calculate it. How do you?
I think it would take the distance, some of the distances between the points.
Okay. I think maybe you want to paraphrase your question so that we'll get the interpretation.
Sir, my question is like a shape is a polygon, and let's say for a country normally the shapes are irregular.
Yes. Yes. Yeah. Polygon can be irregular.
Irregular.
Yes.
Now to calculate the area,
Yeah.
like in the data table we don't have anything specific
Correct.
to calculate the area.
That it was not in the table, but now in an object-oriented framework. Okay, so this is one other transition from relational database to object relational database, right? In relational database, there was pretty much no code there. Your tables were passive data.
Yes.
If you wanted code, you could embed it as a stored procedure or integrity constraint. Okay, but when you come to SQL3 in an object relational world, now the code and the data live together in the database. And the way it happens is in 2 steps. Okay. I did not show you the create type statement, but very much like in Python or in Java, you will create a class, and class will have both data members and member function. Same thing is now true in SQL. You can create type called, create type point, and inside you can say, look, it has X coordinate, Y coordinate, but it has bunch of methods like distance. Same way in the polygon class or create type polygon, you will have its boundary, but you will also have methods like area. Right? And just like Java or Python, you will have a header and you will have an implementation,
Understood.
right? So in some sense, a small part of your ArcGIS or a geometry library has come together with your relational database. Okay, so this is a shift in the database world, right? Does that help? So basically, the code for this method is part of the database now. Does that help? Yeah.
Understood.
Good.
Because
Good.
polygons is irregular, shapes should be irregular, so there has to be too specific to.
Yes, you need those algorithms in there. And for a concave, non-convex polygon, it is an interesting question. What are the best algorithms to compute area, right? So you could use convex hull, but there are different ways to compute area. You could triangulate it, and because we know how to compute area of a triangle very easily, right? It's cross product. So if you triangulate it, then you can add it up and so on. So there are a number of algorithms.
So something what
Right.
say use 10 and calculate the area that means. I'll
Yeah.
just give you
Right.
a-
So this is the difference between when you are in GIS, you are in a procedural world, right? Unless you do point and click, then you are again declarative. But if you are looking at the code, then in GIS, in Java, in Python, you have to choose algorithm and data structure. So I will use one other analogy for people who are new to SQL. Okay? This is the analogy with driving. Okay? So many of us drive automatic right, cars. Previously, we used to drive manual cars, right? So in the manual car, we have to choose the gear, right? So when you are starting from standstill, you choose a lower gear, then you go to higher gear. But in automatic, you say drive, and the car chooses the gear. It's the same thing. SQL is automatic drive. It chooses the algorithm and data structure based on the size of your data and the nature of your data. But if you're writing code in Java or Python, which is ArcGIS, the old AML, then you have to choose those algorithms. If your data were small, maybe linear search was enough. But suddenly it became widely popular. Now you have to switch to binary search or search trees. But it's the programmer's responsibility to do that in Java or Python. But in SQL, the database vendor, or in this case, the third-party library vendor, will have actually a collection of algorithms will come for each of the building blocks. And there will be a query optimizer which can pick and choose, just like automatic drive, right? So people who are new to SQL, that analogy may be helpful, okay? So sometimes people call languages like SQL as fourth generation language, whereas Java, Python are thought of as third generation languages, right? They all have their pros and cons, but as I said, from communication conciseness perspective, this is a much more concise way to hopefully convey. Any other questions, issues? Yeah. Yeah.
Support three-dimensional polygons as well, or three-dimensional figures as well?
As well. Okay, very good question. In the OGIS simple feature type, there is no 3 dimension. It's only 0, 1, and 2 dimension. But as you can imagine, once you have object-oriented SQL, other libraries can be added. So Oracle Spatial certainly has a 3D library. Okay, I'm not sure if PostGIS has one. Anyone more familiar with PostGIS? Have you seen 3-dimensional? Not yet. Okay. But start after mid-90s, there have been attempt to create more spatial libraries, but none are as popular as that. But if you were in specific environments, you will get many more. Okay. But you do have spherical 2-dimension and you have a flat 2-dimension. Okay. Other questions, issues on this?
How can angular or ring-shaped regions be encoded?
It's not built in, but remember it's object oriented. So if that shape was of great interest to you, you could create types, you could write your own library, and the database is extensible, so it can be added through your custom work. Okay, but OGIS simple feature type is simple, right? Just one 0-dimensional thing point, 1-dimensional thing is a line string, and 2-dimensional thing is a polygon, right? Okay, are the other good questions, issues? Again, same way raster support is not there in this standard, but there is an array standard, that some of people have adopted, which is adding that. Good. So we'll come to some other limitations at the end, but let's look through. So first, we now a very simple operation, unary operation. We know how to use it. Let's go to binary step by step. Okay. So now we are looking at distance. Okay, binary operator. And in this case, we are looking at capital city of a country and a fixed location, that's equator, just to mimic this. Okay. So, so essentially, here is sort of, okay, this should be actually this looks like city name, so this should be CI, okay. City is GDP and then distance from capital, okay. So we took country and city, because the capital city information is here and country information is here. Join, okay, capital city. And now we are going to show how to use distance, which will come in the select clause. Okay, so distance typically takes 2 arguments. So one came from the city, this is the location of the city, a point, and this is mimicking the equator. Okay, this is mimicking the equator. We are assuming that your first coordinate, this will be the latitude 0 and longitude is borrowed from the city. Okay. So it's a very simple way to mimic equator, city's location and the distance operator. Okay. So again, syntax and so on, right? Everyone comfortable with what is going on? Okay. All right. Okay, and again here itself you can see some syntax different. If you were in Java and so on, you might have actually called this method on this object. Okay, so that but the general idea is distance should take 2 parameters, and somewhere we are implicitly saying reference system has been specified. Okay. All right, so these are the simple operators. Let's carry on. And here is again a quick one. Now we are going to relate rivers to countries. And we are going to go look at topological operation. And this is now example of a spatial join, right? There will be 2 tables and we have to match them through spatial join. So quick recall, and then we are going to go through the examples. So topological operation, let's take a guess, which one will we need to list rivers flowing through Argentina? Okay, how many vote for touch? Okay, contains, equal, cross. Okay, most of us. Okay, good. So again, your English intuition will take you quite far. As I said, a few small things will show the difference in the next set of slides. All right, so let's go to multi-table queries and think about spatial joins. Okay. All right. So we already looked at area and distance, as I said, and now we are going to look at these spatial joins through primarily topological operators. Although you can use distance also for joining. Any binary operator could be used for that. Okay. So let's look at the simple one. And then we'll also look at a few metric ones. Okay. So you probably anticipated, this query. So we are looking at river table, countries table, and pair rivers and with countries if they are flowing through. And we already know which topological operator to use, which is cross. Okay. So in this case, 2 tables, okay, river and country, and then this is your condition. Okay. So you take river shape, country shape, and we are using cross. Fairly intuitive. And depending on your software, some will say, well, with true, others would you drop this and simply write cross. Okay, the small variations. All right, everyone comfortable with this? Any surprises, issues, question? Okay, pretty intuitive. Okay, good. All right. Okay, so we'll show you a few other examples, then we'll go to the mathematical one. All right, now we are looking at countries and the neighbor relationship. Okay. So this is where your alias question will come in handy. Okay. Because now we have to pair countries with countries, right? And which topological relationship are we looking at among countries? Touch. Okay. So it's a self join. So we are looking at all the countries which are neighbors of a particular country. So, but country has to be used twice, right? And by aliasing, we can refer to individual countries. So this case we are look at the first copy, and the way we are going to relate them is by touch. So these 2 touch. Okay. All right. Good. Any questions, issues? Everyone comfortable with the syntax? Okay. And I said, if you're coming from Java, Python, any object-oriented world, this will feel fairly natural. Okay. Okay. And then the last condition that we are looking for neighbor of a specific country. Now, by the way, this is something you can do pretty easily in GIS as well. You will select a country, highlight it, and all the neighbors can be lit up through a menu system. So this is not showing you a big power yet, but the next one might. Okay. Okay. So let's show a few more examples. So here is a river, and we want to now put things within 300 kilometer and find all the cities which are within 300 kilometer of St. Lawrence River. Okay. You could use a buffer. Very good. For a computer scientist to use buffer is great. But if you didn't want to use buffer, what's the other way you could do it? Distance. Okay, so you can do distance join or buffer join. Okay. If you did buffer, then we'll need a topological operation as well. And which one would you use? So there is a river. I put a buffer of 300 kilometers, so I got an area, and the city should be within that buffer. Okay, within the buffer. Yeah. So okay, so city name. Okay, 2 tables within. So here is the buffer. We had created a buffer of 300 kilometer around the center line of the river, and this city is within the buffer, right? So this is the way most geographers will write it. And as I said, you could have also written it using distance. Okay. Yeah. Okay. All right. So now we are going to create, a little bit more variation. So this time you are doing aggregation, right? Count. So this is a statistical one. So basically some group by and those things will show up. Okay. So again, since we are looking at countries and neighbors, it's a self join. You just remember that query. So that should be very easy. So 2 countries joined by touch. And then what else do I need? Anything else do I need?
Aggregate. First aggregate, then.
Aggregate is usually, order by is to sort the result.
But first you have to aggregate.
Yeah, so which is the group by clause, group by. Okay. So you group by country, and then for each group you basically look at the count of neighbors. So if you were looking for, which country has highest number of neighbors, this query might help you. Okay. So if you order it by that, the top one will come. Okay. Great. So that sort of is the intuitive part. We can make it a little bit more complicated by, nesting and things of that kind. But my feeling is that, we'll probably have more interesting things if we went into the, the mathematical underpinning of these operations. And that's where you will see some more interesting part. Okay. So I'm going to skip the next few examples. If appropriate, we can come back to those in the tutorial as an exercise. Or if you are more into, if you know nested queries in SQL, you can go through some of those. Okay. But I'll pause here. Any questions on the basic syntax of how do you use OGIS operations and data types in there? All right, so I'm just going to skip through this slide. We'll switch to a second deck. And so this, let's not worry about nesting. All right. Okay, so I'm going to skip all of this and I said, let's go to the mathematical part. Let me switch the slide deck. We'll go over one or this one if you like. You can distribute it, but yeah, sure, you can distribute it, and I'll start the last topic. Okay, great. So we are distributing this intermediate course evaluation form. So please take a few minutes in the break and tutorial to fill it out. And I'm going to kind of go under, talk about the mathematical basis for OGIS standard. Okay. So let's try to understand those operations. They look very intuitive, and there is a reason for that. In SQL tradition, we always try to choose names and other syntax and so on to make it very, very easy for a broad audience. Okay, but it's good to know the mathematical underpinning to avoid a few minor, surprises. So broadly, this, OGIS simple feature types follows what we call the object model or vector model in terms of GIS vocabulary. Okay. And it's pretty natural to most computer scientists, because if you're coming from Java, Python, you are sort of in an object-oriented framework. Okay? This is in contrast with raster or field model, which we are not going into for a while. Okay? So objects usually are things which are identifiable. So there are many things which have names, and those are natural to be modeled as objects. So if you think about buildings which have names, right, like this particular building and so on, those can be thought of as objects. So you may wonder, are there things which are not natural to model as objects? Okay, and those in geography, they tend to be there everywhere. So for example, if you think about elevation field, right, how that terrain varies, not every elevation change has a name. So for example, in JNU also you have quite a bit of elevation ups and downs. But do you have a name for every little place where elevation goes up or down? Probably not, right? In fact, there is a very interesting movie some of you might have seen. This movie is named The Englishman Who Went Up a Mountain. Who went up a hill and came down a mountain. So in surveying, mountains have a specific definitions, and they have a list, where you name them, right? So anyone knows the definition of when an elevation is considered a mountain? What's the threshold? Any guess? Yeah. So hill versus mountain, what separates the two? Okay, pretty close. 600. It's about 2,000 feet or 600 meter. Okay. In India, there are many places which are much higher than that, so we are not as worried about it. But in Britain, actually, there are not that many places which are that high. So they actually maintain a list of all the mountains there, and it's given to the tourists so they can go and enjoy it. So the story goes that there is a land surveyor who has to periodically go and check the elevation of this. So he goes to a village which was listed as a mountain, and he surveys it and finds out that there was a slight error and it's not meeting the threshold. It's about 10 feet short. And while he is there, actually villagers find out about his measurements, and they get very worried because they are going to lose all the tourists. So they start kind of going to the bottom of the hill and bring dirt in the buckets, and they start depositing it on the top so that they can meet the threshold. And then rest of the story goes like Bollywood, where this surveyor has a conflict, but he falls in love and he lets it slide and whatnot. But anyway, in elevation, or same thing happens to water features. If you think about, not every stream has names, right? Only the big features like rivers have name, okay, and so on. So there are other models. In geography, there are a lot of amorphous things we have to model for which objects are not suitable. So they do field or raster model. Okay, so that's just to situate ourselves. But in OGIS simple feature type, we are thinking about objects. Okay? They have attributes, operations, and so on. So for example, in this case, these are the attributes, and so on. And then you can attach methods or functions as well. So I'm going to go a little bit quicker to OGIS part. Let me actually see. Let me maybe click through this and go to the OGIS part. Okay. All right. So in object, you can have different kind of properties. The one which we are interested in are the spatial properties. Those are the footprints. So, we can essentially divide them by the dimensionality. So, 0 dimension could be a point. So, oftentimes in a large scale map, a city may be represented by the center of the city or a point. It may be 1 dimensional, like, line string. So, if you have a river or a road in a large scale map, they may be represented by center line. And then finally, you have a 2-dimensional thing like a polygon or a surface. So, states or country boundaries may often be thought of as a polygon. And a lot of time the choices depend on the scale. If you are in a very detailed map, even a city may be thought of as a polygon rather than a point, and so on. Okay, but these are the 3 basic types which are supported through OGIS. And then you have a few other variations like collection of points. If you have a wind farm, you may view it like that, or a set of oil wells. You may also have a multi-string, right? So if you have ever seen the delta of a river and so on, they are a collection of line strings. Or you may have multi-polygons, which is collection of islands and so on. Okay, so these are your 6 basic data types. The 0 dimension point. Okay, 1 dimension is actually line or line string, polygon, and then you have these collections here. So this is your basic class hierarchy for simple feature types. This is showing you the inheritance. So geometry is divided into basically 4 different parts, and then under each you have this one. Okay. Now, in addition to this, there is one other part which I will show briefly, which is the reference system. So any data set that comes in this standard should document its reference system. Okay, and you have an operation. Remember, there was an operation that you can query and find out which coordinate system the data was in. Okay, so let's quickly recall the coordinate system. Yesterday we had a very long discussion, so we are not going to go over that a lot. But as you know, a simple model of Earth is a sphere, which is that latitude longitude is based on that. But a better model of Earth is a ellipsoid. Unfortunately, there is no unique ellipsoid. There are over 180 or 160 around the world. In South Asia, we heard the Everest ellipsoid is very popular. But the main thing when you get the data set, always look at the source. Okay, if the data set is being produced by an Indian surveying agency, chances are they are using the Everest coordinate system. But if it is being produced by, let's say, Chinese system or by US system, they may use a different one. Okay, so that's where this is important. And of course, there is even other kind of things which are based on, other even more detailed system. That's all I will say. Okay, let's now go look at the operations. And we have already seen different kinds of operations. We can talk about set-based operation, which is something most of us know. So suppose you had two polygons, East Germany and West Germany, and then they had a merger, so that can be modeled as a set union, or you can have similarly intersection and so on. So this is one family. Another family is topology based, where the operations like touches inside and so on, and these are invariant with respect to elastic deformation. And then you can also have direction, the metric operations, and distance and so on. Okay, so this is the type of operation you are going to see in this. But interestingly, the topological operations have been chosen in a very interesting manner, and that's what we are going to focus on now. Okay, so this is showing you the complete list of operations. We already saw some of those, like buffer, convex hull, and these are the set operations. This is first time a visual one. So if you have a straight line and you want all the points within a certain distance, the buffer shape looks like this. So here lines are parallel to this, but here it starts to curve based on this point. Okay, this is showing you a convex hull. If I have a set of points, maybe like windmill, you put an elastic band around it, and it will give you the convex hull polygon. Just to give a few examples. Okay. Then you have a few other basic functions to take out things like reference system or bounding box and so on. So if this is a irregular polygon and you do this bounding box, this is what you get, where with sides, rectangle with sides parallel to the axis. And as I said, this has a lot of algorithmic relevance. In computer science, we often use that. Okay. Then you have these topological operations, and we are going to go over the mathematics of this a little bit. But looking at this, let me actually ask you, can you see the difference between within and contains? Okay. So it is sort of symmetric of each other. If A is within B, then you will say B contains A. Okay. So it's just the directionality. Another thing to check is the difference between this let's see, intersect and overlap. Let's see, do you have overlap? No. Yeah, overlap and intersects. What's the difference?
Intersection is a condition for overlap.
Right. So basically, even if you do touch, okay, if you let's say touch, then intersect will stay true, but overlap will be false. Okay. So slight difference. Okay. Okay. And then you have a few other in terms of dynamic one and so on. Okay. But let's ignore these. Now the topological operations were based on a very nice mathematical model, and we are going to understand that a little bit more. Okay. So first thing is that these relationships were considered very fundamental. So in order to design this standard, people looked at the requirements from more than a dozen applications and try to distill it down to what are the common things. And one thing they found was this topological operation. They felt that many applications can use it. So, so as I said, if you look at planar map or you look at spherical map, if India and China are a neighbor here, they are neighbor here. It does not get distorted, right? Same thing, New Delhi is inside India in this map as well as that map. Okay. So they are not, the map projection does not affect topological operations. All right, so and there is a branch of mathematics which studies these kind of relationships. Okay. So let's try to formalize these relationships using this mathematics. Okay. So in topology, the very first set of concepts that you can talk about are these three basic concepts, okay? Interior, exterior, and boundary. So these are sort of like in terms of sets. So if you suppose think about an object A and B in this universe U, then for object A, the inside can be thought of as this red part, the blue line is the boundary, and everything else is the exterior. The same way for B, you can define a green area as inside, purple is boundary, and then this red and white is the exterior. Okay, so this is a very simple way to decompose the objects. Okay, all right. Now if I want to study topological relationship between two objects, then I can look at the three component of A, inside, outside, boundary, three component of B, inside, outside, boundary, and take pairwise combination. So this is A, this is B, and I make this matrix. So look at the pattern. This one I have kind of shortened it. In is interior, BO is boundary, X is exterior. So this row is looking at interior of A, boundary of A, exterior of A. This is saying interior of B, boundary of B, exterior of B. Okay. So I basically look at all combinations. 3 by 3 is 9 intersection. And this is is the basic model, mathematical model underlying all those topological operations. So when in doubt, if you go back to this model, you will resolve that. So we'll come back to Vatican and Italy and sort it out. Okay. Now this was done through a thesis, Max Egenhofer's thesis. He basically say, okay, if I look at these intersections and treat each intersection as a Boolean, which means it's either true or false. Then I'm going to get only so many possibilities, and he narrowed it down to 12. Okay. All right. So first let's look at the binary version of this 9 intersection matrix. And in this example, in A and B interior intersect, right? Because this point is interior of both A and B. So this is true. Let's also check a few others, like boundary of A and interior of B. This blue area, does it intersect with green? No. So that's false. And so on. Okay, so you can verify a few other. If I look at this one, interior of A and exterior of B. So this red area and is also can be part of exterior of B. So true, right? So you can verify each of this pair and make a matrix like this. So original Max Egenhofer's thesis, they had Boolean matrices, and this is the way they represent things. Now you can first ask how many different matrices can be created of this nature. Okay, so just maybe talk to your neighbor for 30 seconds and we'll come back and just kind of think about this. Okay. So again, what we are asking is that here is a matrix of 9 elements. Each element could be either true or false. How many distinct matrices are there? It's a very simple combinatorial one. So how many vote for 9, 18, 81, 512? Okay, great. So there are about 500 or so possibilities. But it turns out that not all of them are actually possible in two-dimensional space. Max Egenhofer went through all 512 of them. And then he also noticed that many of them actually, for most application domains, the distinctions are very minor. So he actually condensed all this to about a dozen group, okay? And those are what is supported by OGIS, okay? So I'll show you a couple of those very quickly. So this is one situation, and you probably know the name of this, okay? Which operation is this? Disjoint, okay? And this is sort of the signature of disjoint, and you can verify it, okay? This is another situation. So I'm slowly moving B towards A, and which operation is this? Touch. This is the signature of that, meet or touch, okay? If I keep moving B towards A, now it intersects or overlap, okay? Now this is also intersects actually, right? This is both intersect and overlap, and this is the signature of that. And if I keep moving B towards the center of A, now it's possibly within, okay? But there are two actually variations of within. Here the boundaries, if they intersect, then it's called covers. If the boundaries don't intersect, it's called contains, okay, or within. So within or contains, The difference is whether the boundaries intersect or not. And finally equal. Okay. So this is your sort of core part of your 9 intersection model topological operation. Okay. And some of these operations also have their dual side. So for example, contains, if I flip it, then it will become within, and if I flip this, it becomes covered by, right? So about a dozen. But these are your core signatures. Now let's try to apply this to Vatican and Italy. Okay, remember Vatican and Italy, I was saying in English, a lot of us will say Vatican is inside Italy, but OG's simple feature type disagrees. So let's figure out what will this say. Okay, so let's first create the matrix for Vatican and Italy. And first thing you may want to check is, do the interiors intersect for Vatican and Italy? No, right? If they don't intersect, then you have to kind of, so let's start from that. So interior intersection, okay, where is interior? Okay, this one. That is false. So what does that leave out? So if this is false, what are the possibilities? Can it be this? Can it be this? Can it be this? Can it be this? No. It leaves us with exactly 2 choices. Right? It only leaves us with just 2 choices. And how can we separate the 2? We can maybe look at this middle element, boundary intersection. Is that true or false? Vatican and Italy, boundaries, do they intersect? How many think the Italy and Vatican boundaries intersect? Okay, how many think yes? No? Okay, a lot of us think. So again, remember the map, remember the map here. So Italy's boundary is this outer one, but as well as this inner one, right? And the Vatican's boundary is this inner circle. Does that make sense? I'm just thinking in India whether we have a similar example, But the Vatican's boundary is also boundary of Italy. Does that make sense for us, right? Yeah. Vatican's boundary is simple. It's like a nice simple polygon. But Italy's boundary is a polygon collection. It has this outer coastline and the interior thing around Vatican and some islands and so on, right? So what do we think? The boundaries intersect or not? Yes. Okay. So is it this or is it that? Meet. Okay. So they are neighbors. According to simple feature types, Vatican and Italy will be neighbors. They are not going to be contains or within. Does that help? Okay. So occasionally when you are in doubt, check the 9 intersection model and that will give you a more precise thing. Okay. Any quick questions, issues on this 9 intersection model interpretation? All right. Okay, so I'm going to show you a little bit more. It turns out that the OGIS simple feature types actually uses a little bit more complicated model than this, and there is a good reason for that. Okay. So again, Max Egenhofer tried to also simplify things. So there are spatial relationships which cannot be disambiguated through the Boolean 9 intersection model. Okay, so you should know that it's not the perfect best model. So here is an example. So if you think about the relationship between rivers and states, then in US you will notice that a lot of state boundaries are defined by rivers. I'm not sure if that happens in India or not. It's more linguistic here, right? Whereas in US and many other places it was based on geographic things like rivers or latitude lines and things like that. Okay. So for example, Mississippi River, some of you might know, it actually starts in Minnesota. And it also defines part of the boundary of Minnesota. Okay. So if I want to look at the relationship between rivers and the lines and polygons, I want to separate 2 types of relationship. One is this relationship. So this river, notice it originates in Minnesota, but it just cuts across the boundary at one point. It does not define the boundary, right? Whereas this river also defines part of the boundary. Okay. Now this kind of distinction is hard to make in the Boolean 9 intersection model. Okay, you are going to see basically the same signature for this river as well as that river. Okay, but if you want to distinguish it, so as I said, this is the signature, same signature for this river and that river with Minnesota. Okay, but if you want to distinguish it, you may have to enhance the model a little bit. And here is a one variation which is used by simple feature types. And what it says is, We are still going to look at 9 intersections, but we'll allow the element values to be little more general. So not just true false, but we will allow it to be dimensional. So if they intersect at a point, I will write 0. If the intersection is linear, I will write 1. If the intersection is two-dimensional, I will write 2. And then I can also write false if you like. So the same 2 example, I'm basically going to say, well, let's first look at the Mississippi River in Minnesota. And so this is one signature. And if I look at the other river, Des Moines River, this is the other signature. And first see, is there a distinction here? Which element do you see is different?
First row, second column.
Okay, so second column and the top element, right? Okay. So let's try to see what does it mean. So I'm looking at interior of this river, Mississippi. So Mississippi is a linear thing. So its end points are its boundary and everything else is interior. All right. So this whole thing is interior of Mississippi. So interior of Mississippi.
So once again the interior part.
Yes. Okay.
The whole thing will be interior of Mississippi.
Okay, so for lines, if you think about a simple straight line, its boundaries are the 2 end points, right? And all other points are in interior, right? So in case of a river, your origin, this is where you have the headwaters from Lake Itasca, that's boundary. And in New Orleans, when it ends, it's a boundary. But all other points on the center line of river are interior, right? So over here, we are in the interior of the river, right? And this interior is intersecting with the boundary of state of Minnesota, right? Which is what you're looking at here, boundary of Minnesota and interior of Mississippi River. And that intersection is a linear thing. Whereas in case of Des Moines River, this intersection is a point, right? So by making this 9 intersection model little bit more sophisticated, instead of a Boolean element, if I look at dimensionality, I can start separating some more situations, that's all, okay? Still, this is not the end of the world. You can make it even more, richer model. But this is the model that's used in your OGC simple feature types. It's called dimensional 9 intersection model. Okay. So now what you are seeing, this is called dimensional 9 intersection model. And all it means is that for every intersection, I'm going to write the dimension 0, 1, 2, or false. Okay. So that's mostly your mathematical underpinning. And if you wanted to actually understand what the OGS implementation is giving you, you probably want to use this particular matrix. Okay. Good. Any questions on the dimensional 9 intersection model? Okay. All right. Everyone comfortable with this? Good. Okay. So the last part I'm going to tell you that even though I showed you this in context of SQL, this library has nothing to do with SQL. You can take this library simple feature types and use it in Python or Java, and there are implementations around. So this should be pretty obvious to you. And I'm just showing you a little piece of code here, which is in Java, but you can start seeing these OGS predicates and things of that in here. Okay. So these libraries now are widely available, and you can use it in many languages. Okay. That's all. Okay. Okay, so this is where I want to pause. That's mostly what I wanted to discuss. And next, we'll go to this, review quiz kind of thing. Okay. So again, last call. Any questions, issues that we had on OGS simple feature types was the main topic, and we saw that in 2 forms. We saw the syntax, primarily through SQL, and we saw a little bit of mathematical underpinning as well through the 9 intersection model. Okay. Yes. Right.
In this OGS syntax, we got point line polygon. Now, when you put it in a database,
Right.
so it has to have a reference
Frame.
reference frame,
Yes.
and the point, the grid point or whatever you call it.
The latitude, whatever your coordinates and everything. Yes. Yes.
So how does that fit into this? Because what is happening
Right.
is we are talking only about a shape, right?
Yes.
So
Yeah.
either it gives you all the 4 coordinates for a rectangle,
Right,
that is
right,
in a database,
right,
or
yeah.
the number of vertices which are there. So
Right.
in the spatial database, how do we fit that?
Okay, so let me interpret your question. So again, this is an interesting transition for people who grew up in GIS tradition. Okay, the computer scientists who did not know the details of GIS, for them, life is simple, okay? But if you came from GIS, this is how the data used to be stored in past. So everyone should remember that, right? So you remember the ARC info, that, the old software? Back then, if I had to store a polygon, then I had to split the information in two parts, okay? The geometry went to something called shape files, okay? And it is still a very popular format, so it's good to know the name of that. ESRI and its users often publish data in shapefile format. So shapefile had the geometry, okay, and then info, the database, only had the non-spatial simple attributes. So for example, the country name, okay. So the simple attributes were kept in relational database. Back then it was some kind of DBase 3 or some of those files. But all the complicated spatial things like the line string, the polygon, they were kept in shapefile. So there were these two worlds, and they were connected through a very simple foreign key primary key relationship. So shapefile will give you a key that you keep in your table. So that way your software could link the two together, okay? This used to be the life, because databases were not sophisticated enough. They wanted your third normal form, so they didn't want to deal with these complicated things, okay? As I told you, the world started to change in 1994, when at least through ODBC, they said, okay, even though the non-spatial thing is in database, I can use Oracle or NDBF, okay? But by the time you reach, this OGIS standard, which is late 90s, and certainly by 2003, people don't have to now keep things in two places. You can keep your complicated polygons inside database table, okay? So once we are in SQL3, there is no longer this separation between shapefile and the simple non-spatial properties. They don't have to be stored separately, at least from your programming and logical perspective, okay? For performance, how I do it physically, that's a different matter. In databases, we separate how you implement versus how you specify, okay? So logically, imagine that they are all in one table. So when I do a row in country table, when I set the shape ID 33, it doesn't have to be a foreign key to a shape file. Your whole polygon logically is sitting right there.
No, but
Okay.
the georeferencing I am saying. for that.
Right, yeah.
So will that also form part of that polygon which is sitting there? The
So you can imagine that polygon has some metadata as well, right? So think about your shape file. A polygon is just a sequence of vertices, right?
Yes.
That node arc area model. But in addition to that, imagine there is a little bit of metadata as well, which tells you that the points in my node arc area model are referring to latitude, longitude, a spherical system. Yeah, okay, so you can imagine that those all are there logically, right? So every row, every line string, every polygon comes with its metadata, okay? Now implementation wise, it's a different argument. Computer scientists will say, oh, maybe I don't have to replicate in each row. I can put it in the table schema. So when I did the create table, and then I can say, look, in this table, every polygon, line string, and point is going to use average ellipsoidal coordinate, right? But that's a matter of implementation and efficiency. But as far as your programming and use is concerned, you can imagine that every object knows its reference frame. Does that help? Yeah. It's a little shift from GIS world to this world. But this is where the interdisciplinary and multidisciplinary really matters. Yeah.
When we talk of polygons in GIS, you
Yes.
have to give the coordinates of, let's say, line has to have both the end coordinates.
Yes.
And the polygon has to all vertices have to
Yes.
be specified in terms of coordinates.
Yes, and you have to be very careful about ordering clockwise and anti-clockwise. It's a positive and a negative, and that was the world in GIS.
So when you
Yes.
transform it to a data table,
Yes. Yeah.
so as you said, now you don't have to specify the that polygon itself will carry all its data along.
Yes. Yep.
That is, the vertices data will be with that part of polygon.
Yes, and polygon will carry whether it is clockwise or anti-clockwise. It's a positive or it's a negative. All that is now hidden. See, that's where the logical data model and physical data model separation comes in.
Implementation is part 2 of that.
Yeah. So see, this is the main contribution of relational databases. In fact, in 1973, how many of you remember the paper by Cord, relational database paper? Anyone read that paper? Okay, some of you. So if you read that paper, the beauty is the following, and this debate was a very lively debate. So there are two characters in databases, some of you might know. One was Cord. Cord was a mathematician. The other one was Bachman. Anyone remember Charles Bachman? They both won Turing Award. They both were in IBM. Bachman was actually far more influential in 1960s. He invented the codicil model in COBOL. And in 60s, the databases used to follow that model, most influential. But he actually was not a researcher, he was an engineer. He never published a paper, but very articulate, right? Cord was a mathematician, and in IBM, he had pretty much no power back in 73. When he published that paper, this is what he argued. He basically said, using set theory or tuple calculus, I can specify the data semantics at a high level, and I don't need to worry about the logic, right? If you read the paper, there is not a single line of code or algorithm or data structure. And in fact, in 1974, when people looked at that paper, they couldn't believe that it could be implemented on computer and you could get interactive performance. Okay? In fact, DARPA grand challenge in 1974 and 5 was to implement relational model on a computer. It's sort of like today the grand challenge is automatic driving, right, of a car. 74, 75, the grand challenge was to get an implementation of a relational database, right? People like Stonebreaker, who just won Turing Award last year. As you can imagine, his PhD was not in database, right? Because there was no database computer science work. It was all business. He was an architecture PhD, and Eugene Wong, a senior faculty member, came from DARPA meeting, and he said, look, people are so excited about this model, it's worth betting your career on. He dropped architecture, he didn't even have tenure. And he said, okay, I will try to prototype a system. Okay, IBM System R was another one. And by 77, first prototypes started to come, which were interactive, right? Then Oracle became a startup. That's about end of 70s. So it was a huge change in mindset. Okay, people used to write COBOL program, and they used to be procedure. And every time you resorted your data, the COBOL program had to be changed. Okay. When you went to relational, it separated the two. You said, okay, your DBA can deal with whether your data would have B-tree or hashing or whatever. Your SQL code will not change. Logical model was separated from physical model, right? And it's the same thing now is happening to GIS. You don't have to worry about your polygon formats. But you are saying, look, there is a logical data type called polygon. There is a function called within. And it's up to your software developer to figure out how they implement it. I don't need to worry about it. Okay? So whether you have DCEL or NAA and all those details which the GIS community spent several decades working on, you can abstract away. But there are some people need to know that. If you are working in a spatial database group inside Oracle and you are maintaining the libraries, you need to know that. But vast majority of people who need to use GIS don't, right? Because now you want billions of people to use these things, right? And if you want them to use that, you have to make it simple. And that's what is happening, right?
Because if you permit, sir, later,
Yeah.
what was happening in the digital map designing in this country, we were working on 3 layers.
Right,
The TIFF, the elevation, and what was called the
Right.
design file.
right.
Design file had all these vectors.
Yes, yeah,
And they were in a way
Right.
georeferenced with the map layer.
right, right,
So it was very easy to pull out a polygon in that.
right, right, yeah,
But as you clarified, when you put it to a database,
Right.
then I think the polygon comes with all its vertices and the way the coordinates is going to land.
right, right, yeah, yeah.
We pre-worked on that.
Yeah, yeah. So I think that's it. It's interesting change of mind. But as I said, if you want this to be a popular technology, you want everybody to use it, you have to make it a little simple. Yeah. Any other questions, issues before we go to the review? Okay. So, it's very interesting, as I said, for geographers or GIS who have actually seen all the gory detail, how sausage is made, this is an interesting change in perspective, okay? But for newcomers, it's probably a welcome change, that's all. Okay. All right, so let me show you the quiz, review quiz, and we'll go there. So this one, I'm not sure if we have copies. So if you have your laptops, maybe open this and let me see if we have copies of this. Can I take a look just to make sure? Oh, this, okay. So this is from yesterday. Yeah. So do you think you can make copies of this one? This is. Today I should have told you before. So this is the review quiz 1. Okay, so you can take a look at this one and see if you can make copies. This is on the web. This is this one. This one. Actually, maybe. Let's maybe you distribute this, we'll use some questions. Yeah, just go ahead and distribute it. I can use at least question. Yeah, so I think I will today try to load that early, maybe before I leave.
Yeah,
Okay.
before.
We leave, yeah. And one other thing we have to do is to tell the PCS people about tomorrow coordination. So we should maybe decide and then I'll email them. Yeah. Show them. Okay. So it's a tutorial written quiz one. I don't think we'll have time. This one is enough. All right, so just a small clarification, so based on time, actually, the paper handout that has gone, only couple of questions we are actually equipped to work on. So I'll just, show you the paper handout, which one we can work. So paper handout, I think, is this one, and we can work on one question in this. Not this, yeah. Paper handout is yesterday's, yeah, and that's actually this one. Yeah, this is the one, and the question we are, we are ready to actually work on is question 2. So this is one. Okay, here is the question. So from the printout, just look at this question. All right. Printout, only look at this question. And then on the other quiz, I will, I showed the first 2 questions. I will show a few more, and we'll work on those as well. Okay. this point to that point. Either of end point show up on this rectangle. Inside, but not inside, but not on the boundary. So, right, so this is false. Yeah, so I would usually fill out these four first, they are most important. This tends to be messy. So one of the boundary, one point is so boundary. Same way you can now start. Yeah, so at least fill out these 4 points. That's where most of the information is. So if you think about it, so you have to first also remember the So if you think about this, this two looks good because if there is this point which is not here. But if you look at, for example, this is also this one. If you look at boundaries. Oh, two parts I understood. Oh, very good. Thank you. Yeah, please. Okay, so we now have a copy of this quiz, and I will suggest skip question 10. You don't have to write the code. And the second part is more spatial, so you may want to kind of work on the from question 4 to question 9 are the most interesting. Okay, so on the other quiz, just look through 4 through 9. Okay? Yeah, then whiteboard use the maybe there is a switch here.
No, I think it's all manual.
There are some of this you don't like this.
Oh, yes.
Sir, I am calling.
Oh, okay.
This gentleman, can the screen go up?
ये हाँ खाली वाइट बोर्ड यूज करने की ओके ये बटन अप बटन तो यहाँ पे है एलसीडी तो ऑफ हो जाएगी एलसीडी में प्रॉब्लम नहीं है ओ अच्छा वो आपको प्लग इन करना
Basic connection was not there.
अच्छा अच्छा या कर दीजिए प्लग इन कर दीजिए सस्ती
क्या करना है सर?
We tried the button, but we didn't check whether the switches was plugged. नहीं, केवल व्हाइट बोर्ड एक्सेस करने के लिए वो तो दिखाई दे ही रहा है टू एक्सेस द व्हाइट बोर्ड that's all. Thank you. Okay. Actually, it's on his website. You can see that one. So from there you can take it.
First difference is you compare against it.
extent in the coordination.
Okay, so, alright, so okay, not to make it complicated, but at SQL level, it is in the SQL level, the logical level, it is in the table. So if you are writing SQL code, just assume it's whole polygon is to be right here, and you can do all things. So as a programmer, you don't have to worry about.
No, I'm talking about the JS context. Now we say polygon, we say JS. Now the coordinates.
It's not yes, actually, it is actually an object. And inside the object, you have all the coordinates.
Mark.
So each coordinate, each point has its coordinate.
So I say US.
Yeah, and so you should actually think about this as a real polygon.
All what is not.
Assume that it's true. As a programmer, you don't need to worry about it. But I mean, just to be accurate from computer science perspective, when they store a table, they can still choose to factor the row into two parts and store it in different ways. But that's hidden.
Agreed. Now,
But as far as programmer is concerned, the polygon is right here.
but as far as a JS professional, when I need to use it, so from here itself I can pick it up.
So in your code, you just write it as it is.
Are you worried about to create or save?
No.
I mean, insert a row?
No.
Are you concerned about performance or code working correctly?
I just want to understand, sir, like we say polygon fine, we have the shape. But when you calculate the area and all shape, you need to know the coordinates.
In this case, in object orientation, you don't. You just say this column name dot area. It's system's job to figure out how to calculate.
One thing, but then where are the coordinates to? That is my question.
Okay, so, so I will,
I thought you needed a storage level.
so this is what I will, this is what I'm telling you, the separation of concern. Where it is stored, you should be interested in only if performance, only if it's running slow. Okay, that's the only time it matters. But if you are only concerned about getting the correct result, getting your match working, but you're not worried about whether it takes 1 second or 1 hour, then assume it's right.
Agree. Now, when I say insert, I insert data about yours and I insert the polygon. Again, I have to give it what is it.
You can. Basically, I didn't show you the example, but there is a constructor, a constructor called polygon. In parentheses, you can say point is another constructor. In parentheses, 1, 2, point. You can. So you could actually create. So these are constructors. Java and so on. So you can say point. I'm just giving you a very simple example. So this is all valid syntax. You could this is now a polygon, right? So in your insert statement, you will have table name, column. Here when you have value, you might say the USA country name, but this is your polygon, another value.
So between the polygon column when I will create a table, I have to say listing, outling or whatever.
Yeah.
So that accordingly values fit. That was it.
Yeah, okay. But so that's the simple answer. As a programmer, everything is in your table.
Because as I was studying database and special data, I guess this is the first major distinction that will come into.
So if you that's the thinking in GIS and database is in one place.
Yes.
But the only time you have to go beyond this is performance.
That understood.
Right? If it is taking you 3 hours to run and you don't like it, then you have to talk to DBA to figure out how to store it. But it will not affect your SQL.
Understood.
Okay.
How it is stored, the storage, the type.
Because why this question came up, sir, in the Brussels University Special Data paper, we have done like this.
And I will show you a code example if you want. I can show you. It's let me try to see. Have you had time to work on this?
Yeah.
Top 3 questions.
You said 4 on
Okay, so I will give another 2 minutes then we can start. And you think it's okay to have some students first share their answer and Yesterday I had in a group, so it's very non
Yes, yeah.
But today I want to get specific.
Yeah.
Is that okay? We will discuss. Yeah. But your answer is different. Why don't you publish it? So it's always fun to have two different answers. Okay. Can your group come and publish?
Excuse me, this already experience, so one of the experience. That's why I asked you.
No.
Not yet. Then there is a conflict.
Yeah. So we will discuss it. Okay. But I want. Before I think we should discuss. I want your group or your group. This is like this point is an experience.
Learning by mistakes is the most.
So okay. Well, so it will be good if you want to also
What
publish
about
it.
this line? That is boundary to the experience with this and this point.
Yes. Not experience.
Then you learn it better.
These two are
And cardamom and anyone legality is
this is experience.
unless you make a mistake. We never accepted it. It cannot be perfect in 1000.
Okay.
Draw a line and
Put it on top. Don't. Yeah, put it on top. Only this is the one. Okay. That's the only thing. Okay. Stop it. Good. Keep in standby mode in a minute. So, which question are you working on? Mostly let's say the one left. Let's finish the quiz and we will discuss it. So in dimensional matrix you could have had more value. Maybe you would have six, right? So in zero dimension also you want to see this one point of view. You could, but you have points are still. But the question is the intersection collection of points or is it lines? Lines are important. Linear things are if they are so is that this one question, this green board also can be done. Just have regular
Get the job.
shop, okay, so I'll have like two groups publish. Okay, why don't you come and put another ad?
Second first. Second first. false and false. Yeah.
So, actually, I need some more volunteers for quiz.
Yours too? It's true. Okay, I make it true. Interior of the no. You've got the chalk pieces.
Okay, all right, great, great.
You
This
can
is
put the duster.
duster, yeah, no, this is good, I think I'll maybe found.
In the other classroom, we did have that.
This one, okay, I'll use it. So let me ask some more volunteers. For the quiz, you guys are currently not publish your answers, so just under group one, group A, group C, and so on. Very wonderful perspective.
Thank you.
Okay, so all right, in interest of time, we'll go and have a group discussion, and it may be simpler to first go through the quiz, okay? First go through the quiz. So we have 2 sample answers, on the quiz for questions 4 through question 9 on the board. So first is, you have any other answers, let us know, and we want to put that up and then discuss. So quiz question 4 through 9, are there other answers? Question number 7, okay, what are the other answers? Okay, C. C, anything else?
Sir, question number 6B.
Question number 6B. Okay. Others? Question number 7, also D. Right, okay. And which one?
8C.
Question 8C. Okay, any other? Everyone comfortable? All right, so let's go through these ones. So question number 4, let's start with that. And there is a consensus, we don't have a roster, so that's good. Okay, so I'm just going to use paper. Probably if I project, then that will get covered. So question 4, I think, let's say there is a good consensus that raster is not covered by OG's simple feature types. And as I was telling you, there are other efforts. Particularly, there is a standard called arrays, which has been implemented by several groups now, but it's not as widely available. Let's go to question 5. Which operation is not included in OG's simple feature type? And we all said shortest path. We are going to see that tomorrow. Even though it's one of the most popular operations today because of Google Maps, the OG simple feature type was focused much more on natural kind of values, not on transportation. So, so we are all together here, but this we'll see tomorrow. Question 6. Now here we have some diversity, so this will be an interesting discussion. Which of these operation is not topological? So we have A and B. So how many vote for first A? Okay, well, a lot of us, good. And how many votes for B? Okay, just a couple already. So the way to resolve this is very simple. Remember, topology is defined in mathematics as a relationship which is invariant with respect to elastic deformation. You can test it, think of spherical maps like globes and flat maps, paper, right? Because there will be a distortion. And think about whether, if two things were equal, when we say equal, they are essentially, you take a geometry, a polygon, move it over to another polygon, and it will cover them exactly, right? And which means that